So remember 2.2, 2.3, 2.4 were all different rules that are going to help you get at the derivative as quickly as possible. And 2.1 or 2.2 is your first section, basic differentiation. I wanted to show you guys something. Do you guys know how Pascal's triangle works?
Is that the triangle that you see between the triangles on each side?
No, that's Sierpinski's triangle. Pascal's is the one with the numbers.
Oh, I mean the one and the one, then 1, 2, 1.
Yeah, you do 1 on top, and then you do a 1 and a 1.
Then 1, 2, 1.
You just do ones,
And
yeah,
then 1,
exactly.
3, 4, 3, 1.
So let me draw this for you. You put ones down the side, and then after the second row, you start adding up the ones. So this 1 plus this 1 is 2. Then you start adding up these entries. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. My hand was doing, my brain knew what was going on. So what's cool about this is you can use it to square and cube things really fast. Okay. So what I mean is, let's start with this one because it's kind of the let's start with this one. This one's kind of the most interesting. You can use this to do x plus h squared really quickly. It gives you the coefficients of all of the, I guess we did delta x. You can do x plus delta x squared really quickly. This gives you the coefficients that you get in the result. You get 1x squared plus 2x delta x plus 1 delta x squared. So this gives you the coefficients you get from expanding. So using that pattern, do you think you can figure out what x plus delta x cubed is? Should be 1x cubed. Now what do I add next?
X squared.
You have to start mixing your terms. So it'll be 1x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. See what happened? This guy did give you the coefficients, but you have to go down a power every time. This is x cubed, then it becomes x squared, then it becomes x to the first, then it goes away. I'll show you why. Let me do one more. So x plus delta x to the fourth. We'll start out with 1x to the fourth. Then we move to 4. What? X cubed delta x. Then we move to 6. Then what's the x?
6x delta x.
X squared delta x squared. Plus 4.
X delta x cubed.
X delta x cubed.
Then plus delta x 4.
Plus a single delta x. So why this is kind of interesting is because it can help us find the difference quotient really fast for some of our power functions, for some of our basic. For some of our basic x to the first, x to the second, x to the third functions. So for example, if I wanted to take f of x equals x cubed and find f prime of x, I would have to do the difference quotient with x cubed and then do the limit. So I would have to do f of x plus delta x minus f of x over delta x. But what is f of x plus delta x in this case?
X plus delta x cubed.
X plus delta x cubed. Minus x cubed over delta x. But I know what this is now, right? I have it. It's right here. This guy. whole mess. X cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. So I just copied it from here. Then you minus x cubed all over delta x. And what's my result?
Well,
X cubes go away. Everything else has a delta x left in it. So at the end of the day, I'm just going to have limit as delta x goes to 0. This guy's going to become 3x squared because the delta x will cancel. The delta x cancels here. This guy's delta x squared.
thank you.
So these go away. And all you're left with is 3x squared. So, whatever, if you didn't follow that, you can do it on your own a little slower maybe. But what I kind of want to point out is that you can actually pick out in this expansion where the derivatives sit. Right? X cubed, 3x squared, 3x delta x cubed. The derivative is this guy here. Because at the end of the day, this x cubed went away, and this guy got factored out and canceled, and everything else went to 0. So that's your derivative. What do you think, without doing any work, you're going to get with the x to the 4th situation?
4x cubed.
It's the same pattern. If you went on, this would be a 5, 10, 10, 5, 1. This is the only guy that matters. It's going to be 5x to the 4th. Because everything else either goes to 0 or gets subtracted off. Kind of the generalization of this rule is called the power rule. It's your first differentiation. So if you have a function equal to x to some power, it actually doesn't even need to be a whole number. Just any power. Generalize it. Then the derivative, f prime of x, is equal to n times x to the n minus 1. Right, the derivative of x cubed, what happened is we bring the 3 out front, and then we subtract 1 from the power. The derivative of x to the 4th, we bring the 4 out front and subtract 1 from the power. So bring the exponent out front, and then subtract 1 from the power. That's how you do the derivative if you have x to the sum. X to some non-variable exponent. Let me give you 2 more rules and then we'll use them all in some examples. So these are the sum and difference. And then also the constant multiple. So the sum and difference says if you want to take f of x plus g of x and do the derivative of that whole sum, so this prime here, let's take the derivative. That's equal to doing the derivative on each individual function. So this is the same thing as just breaking the problem up into f prime of x plus g prime of x. So to take the derivative of a sum, you just end up taking each derivative individually. And it's the same thing for minus. There's a minus here. This just comes down to the fact that the derivative is a special type of limit, and limits play nice with sums. Constant multiple rule. If you have a constant multiple, so not a variable multiple, if you have something like k times a function, and you want to do the derivative of that whole thing, so where this guy's a constant, not a variable, it's got no x in it. That's the same thing as just taking a constant times f. So one way I think of that is that constants being multiplied can get pulled out of the derivative. One thing you have to be careful of, so there is a product rule and there is a quotient rule, but they're not as simple as this, okay? Those are the next section. Okay. Products and quotients do not play nicely with derivatives. And I'll show you why in the next section. But sums and difference do. Constant multiples do. One thing you have to be careful of here is what happens when n equals 0. I forgot to tell you that. Back up on this power rule. What happens if n equals 0? Right, if you have f of x equals x to the 0, this is just equal to 1, so what's the derivative?
0.
Just 0. But if you try to naively, because I don't know, you believe everything I say, apply this rule, and you do, oh, well, Josh told me the power rule says I can bring this 0 down, right, and then multiply it by x to the negative 1. 0 over x, I guess this is okay, all right?
It's still.
It's still true, but
Waste of time.
it's not, yeah, it's not, it's a waste of time, yeah. Not super effective, good word. So if you have a constant, any constant, doesn't matter if it's 1 or 12 or 7, what's the derivative? If f of x equals, I don't know, 13, what's f prime?
0.
0. Right? As long as there's no x in your formula, the derivative is 0. Because this is a horizontal line.
No variable.
No variable. Correct. No variable, derivative 0. All right, let's do some examples. Make sure we get this straight. So sums and differences play nice with derivatives, and constant multiples play nice. Products and quotients, we have to wait for next week. I know. I don't know how you guys are going to make it through the weekend. It's all right. So find each derivative. Find the derivative of each function. Start with the baby. x to the 7.
Sorry.
Yeah. If you have to take the derivative of x to the 7, and I don't say use the definition, right? If the instructions say use the definition of derivative or use limits, I want you to do the delta x going to 0 stuff. But if it just says find the derivative with no special instructions, you should just use your rule. So the 7 will come down, and you'll subtract 1 from the power. There's your derivative. Probably die if you try to do this with the definition of derivative, right? You'd have to do x plus delta x to the 7. It's a huge, massive thing. But the pattern tells us it's just going to end up being this. All right? So what about y, the function y equals 1 over x? We just did it, but let me do it with my rules instead.
Maybe 1 x to the negative 1.
Right, so sometimes it's not obvious how you can apply the power rule, but if you do some sort of algebraic manipulation, then you can make it look like x to an exponent. So if you have a denominator like this, you can rewrite it with a negative exponent. This is x to the negative 1 also. So now the power rule applies. The negative 1 comes down in front, subtract 1 from the power. Usually, I guess you can leave it like that if you want. Usually you put it back down. There's your derivative, y prime. Here's the derivative you wanted to do earlier. That I said I don't want to do because it leaves the difference of cubes formula. So I want to find the derivative of the cube root of x, but all I know is my rule if I have an exponent. That's all I know as far as derivatives go. If I have an exponent, I can bring it down front and subtract 1. So I need to turn this into an exponent. 1/3. So the original function is just x to the 1/3. So then the derivative is going to be 1/3 comes down in front, x to the negative 2/3. You have to subtract 1 from the exponent. So you have to take somewhere, if you can't do it in your head, you have to take this 1/3 power and subtract 1. All right, make it 3 over 3. So you get negative 2. That's the way the power rule works. The exponent comes down and then we subtract 1. Again, this guy I would probably write, I would get rid of the negative exponent because it frustrates me. You could leave it like that, that's okay. If you wanted to put this back into a root, what root would it be?
Cube root of x squared.
Yep. Right, the bottom of this fraction exponent gives you the index, so cube root. The top gives you the exponent. So these are all focusing. Make it a little more complicated for you. 3x squared minus the square root of x plus 5. I want to find the derivative.
We do separate ones and the constant we take it out.
Yeah, so the way derivatives work, right, if you want to do the derivative of this whole thing, prime, right, you want to prime this whole thing, do the derivative of everything, you can, because they're connected by pluses and minuses, you can separate it to each term. So you can just do 3x squared and take the derivative. You can just do minus root x and take the derivative. Plus 5 and take the derivative. This is y prime. You still have to do some work here. In fact, this guy has a constant multiple. Right? So when you take the derivative of something with a constant multiple, you ignore the constant, you pull it out front, pull it outside of the derivative. And that was our constant multiple rule. 3 can come out. You can just do the derivative of x squared, which you're a master of by now. Over here, you're going to have to rewrite this guy. What do you rewrite him as? X to the 1/2. And then you do your derivative formula for your power rule. What about the derivative of 5? 0. It's a constant, right? So it's not even right. So I'll do my work here. The 2 comes down, I subtract 1 from the power. So this is going to be times 2x. And then, because I actually took the derivative, I stopped writing the prime. On this guy, the power comes down, and I subtract 1. So 1/2 comes down, and then I do 1/2 minus 1. 1/2 minus 1 is negative 1/2. So this is equal to 6x minus
1/2.
Yeah, if you put this 1/2 back down in the denominator, this is 1/2 of x. So 1/2 makes it a root, the negative puts it in the denominator. Now, this is okay with me. This is a perfectly good derivative to me. I don't know what Larson's going to do. I don't. He might make you, like if you want to match his answer, you might have to get a common denominator and add these up or something. I don't know. Try the homework and tell me what he does. and if you need help with the algebra here, we can go over that. You ask some problems. But for me, that's fine. That's the derivative. So I did this in like gory detail. Okay? But kind of the gist of it is, this derivative is just going to go straight to the x. It's going to take the derivative of the x squared. It's going to take the derivative of the root. And it's going to get rid of this. How come the 3 stayed? You see how the 3 stayed in our answer and then multiplied here? But the 5 went away. 0. Yeah, because the 3 was multiplied. It's a constant multiple. So that guy's going to come out front and stay. But a constant being added is always going to get derived away to 0. So the difference is the operation. F of x equals 2x plus 5 quantity squared. I want to find the derivative, which I'm going to call df dx, just to remind you of that notation.
4x.
What?
4x?
4x? Is that what you said?
Yeah.
Oh no. I don't think so.
I'll just swear it out.
Yeah, you got to FOIL it out first before you do anything. Right? The power rule doesn't apply unless you just have x to the n. Right? Since this is more than just x in here, you have to FOIL this out. So I would do some expanding. This is going to end up being 4x squared plus 20x plus 25. That makes sense? So now you can do your power rule on each of these. Right? On the 4x squared, because the 4 is a constant multiple, it stays, and then you get the 2 coming down front. So ultimately, the final answer for the first part will be 8x. Right? The 2 comes down and gets multiplied by the 4. And you subtract 1 from the top. For 20x, what happens? Just 20. Right? Because this is x to the first. The 1 will come down and get multiplied, but it turns into x to the 0. And x to the 0 is just equal to 1. So altogether, your derivative is 8x So let's do 3x squared plus 7x plus 2 all divided by x. This is your we want to do the derivative. Remember, derivative does not distribute to top and bottom. So if you want to do this derivative, you're going to have to somehow simplify this function. You guys, do you know how you can rewrite this?
3x plus 7 plus 2x, 2 over x.
Yeah, split it up. You can split the fraction up. Yeah, so this is going to become, this is equivalent to 3x squared over x plus 7x over x plus 2 over x. And then each of these reduces a little bit. Wow, except this. So my function becomes 3x plus 7 plus...
Plus 2 over x.
Yeah, let me go ahead and rewrite 2 over x though, because it's going to be hard to derive unless I have an exponent.
2x have
2x to the negative 1. Right, this guy can come up as x to the negative 1. Now that I've rewritten it into something I'm used to, where I just have a single x with exponents in each term, I can derive. Derivative of 3x, just 3. Right? The 1 comes down and you have x to the 0, which is going to go away. Derivative of the constant, 7, 0. You don't even need to write it. Plus, then you do the derivative of 2x to the negative 1.
Negative 2 over x squared.
Right. So this negative 1 is going to come down and multiply by the constant multiple. And then you have to subtract 1 from the power. So this will be negative 2x to the negative 2nd. So 3 minus, bring this guy back down. There's your derivative.
It's kind of weird because if you combined it, it'd be 3x squared minus 2 over x squared.
Why is that weird?
Because when you look at the top, it's 3x squared. So all you did was get rid of the 7 and change it to a plus.
Yeah. Yeah, there's no pattern there.
Yeah, it just seemed weird.
Yeah, coincidental. So a lot of the problems in this section, at least at first, are going to be you manipulating some function so you can apply your power rule over and over and over and then over again. Let me give you one more example, and then we'll get into sines and cosines. Yeah! Woo! Sine and cosine! So here's what I want to do. I'll find the equation of the tangent line. F of x equals x cubed minus 2x at x equals 1.
So we need a form. Oh, never mind. We could solve for it.
No, yeah, you don't need a point. Let's not do 1. Let's do 2.
I don't know how to start.
You don't know how to start? Okay, so we're trying to find the equation of a tangent line, right? To find the equation of a tangent line, the first thing you need is slope of the tangent line. And we learned that the slope of the tangent line is the same thing as the derivative. So I'm going to start by taking the derivative. But I'm not going to do any difference quotient nonsense. I'm just going to say f prime of x, use my power rule. This becomes 3x squared, and then minus 2. We okay with that? So this is the slope of the tangent line for any x. But I want to find the equation of the tangent line at x equals 2. So what do you think I do with this?
Replace the value.
So f prime at 2 will be equal to 3 times 2 squared minus 2. So 12 minus 2, 10. This is my slope when x is negative 1. Oh, I'm sorry, positive 2. Where did I get negative 1? I have no idea where I got that from. Oh, I know what I mean. But
Solve for the y value.
so in order to find the equation of the tangent line, if the problem had just asked for slope of the tangent line, you'd be done. But we need the equation of the tangent line, which means we need not only an x value, but a y value. So let me come back up here and say, well, when x is 2, what is my y equal to? How do you know?
8 times 4.
10.
You plug it into the original function. Right? You plug this x value f into f. Find f of 2.
4.
So then you'll do 2 cubed minus 2 times 2 if you plug it into this function, 8 minus 4. So I have a slope which comes from plugging 2 into the derivative. I have a point which comes from plugging 2 into the original function. Right, my point I know is 2 comma 4. 4. So then I just use my formula, find the equation of tangent. Yeah, do your point slope form if you want. Y minus y1 equals m times x minus x1. So y minus your point here, your y value, y minus 4 equals 10, because that's the slope we got from our derivative, times x minus 2. This is kind of ugly. Yeah, I would probably solve for y. Distribute out the 10, add the 4 over, y equals 10x. So when your problem says find the equation of a tangent line, you're always going to need to find a slope and possibly a point, depending on if they give it to you or not. So for equation of a tangent line, you're always going to need to do the derivative and plug in your x value. That's step 1. Possibly you're going to need to plug your x value into the original function to get a y value. And then you need to toss that into your point slope form to get your equation. I will warn you, although I guess I don't know if you'll heed my warning. Be careful, if I ask you to find the slope of the tangent line and I ask you to find the equation of the tangent line, those are 2 different problems. And if I just say find the slope of the tangent line, you stop here. And you're going to be wasting your time if you go in and do all this garbage. Like on a test, I'm saying. So keep it straight. Equation, you definitely need a y value when you do point slope form. Slope, you can stop right here. I was delaying. I was trying to buy time. I'll have to do something. So I'll show you one of them. Show you why the derivative of one of them is what it is. And then you'll just have to believe in the other one that's right. What we need to know, though, which one do you want to do? You want to drive sine or cosine? Sine. Okay, good answer. That's my favorite. What you really need to know to be able to come up with what the derivative of sine is, two things. Well, I guess three things. You need to remember from trig what happens if you have sine of alpha plus beta. You guys remember this formula? How do I need it? So sine alpha cos beta. For sine, the sign stays the same. So plus sine beta cos alpha. Right, so when you have sine of a sum, you cannot just distribute it. You have to use your angle sum form. And then we also had this. Recently, maybe you remember this. Limit of as theta goes to 0 of sine theta over theta is 1, right? And then we had another one actually. It was like 1 minus cos theta over theta. Remember this one? 0. So with these three things, we can find the derivative of sine. Okay. So I want to use the definition of derivative. Right, be watching for that on instructions. Right? If I say use the limit definition, you're going to do some delta x going 0. But use the limit definition of derivative to find f prime of x, where f of x is equal to sine x. So we're going to find the derivative. Limit as delta x goes to 0, right? We just apply our limit definition. F of x plus delta x minus f of x. So when we plug in our x plus delta x, what are we plugging it into? Sine. So this becomes limit as delta x goes to 0, let's sine the whole quantity x plus delta x minus sine of x, because you subtract your function here, over delta x. Oh, I hear you. Feel your pain.
Then we'll split it.
This guy's going to get split up using this formula that I miraculously have over here for you. All right, this is limit delta x goes to 0. But instead of writing sine of x plus delta x, I'm going to break it up. It'll be sine x, sine delta x.
No, cosine.
Oh, good. X, delta x, so x, delta x. So sine x, cosine delta x, and then sine delta x, cosine x.
Minus 1.
Okay? So what do you think?
That one, it's gonna equal to 1. So
Would
what-
cancel out sine, it would be sine, the cosine with delta x would cancel out and be 1.
Yeah, so let me,
So it's gonna equal sine x plus cosine x.
yeah, so let me split this up where I can.
So sine x minus sine x, and then you have sine.
Hold that for that. Derivative of sine is cosine. So kind of the bottom line here is you take sine and you do the derivative, it's equal to cosine. What do you think the derivative of cosine is?
Negative sign.
Sine,
Why do you say that?
because it would be, the minus would be out there.
Yeah, in cosine, what happens is when you use your cosine formula,
Minus.
there's a minus in it. So this minus here is going to end up giving you a minus in the derivative. Everything, a lot of the other stuff works the same,
It would be negative in the
but you get a negative when you do the derivative of cosine. This is going to haunt you. I don't know why, but it's very difficult for people to remember where the negative goes. I don't know. I just say it in my head. I know the derivative of sine is cosine, and so the derivative of cosine is negative sine. But somehow you have to keep straight which one gets the negative. Otherwise you're going to lose points. If you come up with a good way to keep it straight, let me know. I'll pass it on.
Sine thinks it's better than cosine, but cosine knows it's not better than sine. I don't know where that came from.
Okay.
But I
don't
just
know if that
instantly
confused
remembered
me
it. I just instantly
Alright, let's
remembered
go with
that
that.
now. That's weird.
What, I'm sorry, what was the double angle form, or the two angles added together?
Angle sum for cosine?
Yeah,
Cosine alpha, cosine beta, minus sine alpha, sine beta.
Okay. So let's do some examples. I need derivative. Find the derivative. Let's do f of x equals sine x plus cos x. What's my derivative?
sine x minus sine.
So f prime of x, because it's a plus, I can do the derivative individually. All right, so first I do the derivative of sine, which is cosine. Sine is he's the easy one. But then you also have to do the derivative of cosine, which is
Minus
minus. function y equals 3 cos x minus 5 sine x.
Negative 3 sine x.
So dy dx, the derivative. So now, not only do we have a minus, but we also have a constant multiple. So how's that work?
Take it out.
Just focus when you do your derivative, focus on the guy that has the x. Do the derivative of cosine, what's that?
Sine.
Negative sine. But then that gets multiplied by 3.
Three.
And then move on. Derivative of sine x, regular cosine x, right? So you'll put cos x down here, but the minus 5 constant multiple adds along. X equals negative 2 cos x minus 1 over x. How are we going to do this derivative?
2 sine
You're gonna
or
separate.
2 sine x.
Yeah, you're going to do it in pieces again. Right? The negative 2 cos x doesn't have to be manipulated, but this guy does. What's he get manipulated to?
X with
X to the negative 2.
Yeah, again, you're thinking power rule here. You bring it up to x to the negative 2. Now you can do the derivatives of these functions individually. The derivative of cosine, I know, is
Negative sine x.
Negative sine
negative
x.
2 sine x.
df dx. Because the derivative here is negative sine x, you multiply that by negative 2, and it becomes positive 2 sine x. Alright, so negative sine x times negative 2 is positive 2 sine x. Then you have to do this derivative. The negative 2 comes in front,
But the negative becomes push.
and then it becomes x to the
Negative 1.
negative.
I mean,
Alright, you bring that, the power rule says you bring this exponent down, and then subtract 1 from the top. So 2 sine x plus 2 over x cubed if you get rid of your negative exponent. Super bueno or no bueno? Bueno. Moderately bueno. Más o menos. Find the equation of the tangent line. Y equals cos x plus sine, let's do 2 sine x, at x equals pi over 2. So what do you think?
Take the derivative.
Yeah. If you're trying to find an equation of tangent line, you know you're going to have to do a derivative. Take derivative. that will give you the slope of the tangent line, and then you can go back and find a point and then do your formula. So first we need y prime. So you do the derivative of cosine, which is negative sine, plus 2 times the derivative of sine. So here's your derivative function. But I want to know the equation of the tangent line at x equals pi over 2, so I go ahead and plug pi over 2 into this. So I have to do negative sine of pi over 2 plus 2 cosine of pi over 2. So pi over 2 sine is going to be 1, and cosine is going to be 0. So negative 1 plus 0. So my derivative at pi over 2 is just equal to negative. So this is slope. That was step 1, right? The first thing you need to find is your slope. Now, if you're trying to find the equation of a tangent line, you then have to go in and find your point. I have the x value of my point, which means I need the y value of my point. What do I do?
Plug pi over 2 into the original equation.
Plug pi over 2 into the original function. So you got your slope. Find your point by taking f or y at pi over 2. So plug pi over 2 into the original function, cos pi over 2 plus 2 sine pi over 2. Sine of pi over 2 is 1. Cos of pi over 2 is 0. So 2. My y value. Alright, so overall here the point is when x is pi over 2, y is 2. That's my x1, y1. Finally, I can go to my equation. Might as well use point slope form, I guess. Y minus y1 equals m times x minus x1. Plug in what you know. Y minus 2. Yeah, so I got to go back to my slope here. Equals negative 1 times x minus pi over 2. Y minus 2 equals, distribute out the negative 1, negative x plus pi over 2. Add the 2 to the other side. You can get a common denominator if you want. I don't want to. What do you think? Not bad? So there's the one more thing. One more thing that they kind of go over in the section, which is instantaneous rate of change. Instantaneous rate of change is a fancy way, another way of saying derivative. Let me kind of show you this context. So one very crucial, I guess, application of derivatives is position, velocity, acceleration, how they're related. So let S of t position function. What that means is this is going to be a function that is somehow telling you the position of an object as time varies. It might be its position on the y-axis or the position on the x-axis, but in some way it's giving you a position as time varies. So let me give you an example. So let's let s of t equal 225 minus 16t squared. First of all, do you know what the graph of this function looks like? Upside down for how?
Shift it up.
Shifting up. Shift it up, right? Because if you plug in 0 for t, you get out 225. Quick sketch of this might be where this is your t-axis. So you have different times on this axis. Maybe 1, 2, 3. 1 second, 2 second, 3 second. And the y-axis measures your position. In this case, for this particular type of equation, the position is how far what this is supposed to model is dropping some rock or some object from the top of a 225-foot building. So if you take some object, you drop it off of a 225-foot building, its position relative to the ground is going to be modeled by the y values on this function. So for example, when t equals 1, it's going to be really close to 225 feet high. When t equals 1, you could plug it in here, you get 225 minus 16. So when t equals 1, your object's right here. When t equals 2, it's fallen a little further, but it's fallen more than it originally fell. You see what I'm saying? This distance here is less than this distance here. So it'll be more down like this. Right? Because it's picking up speed as it falls. T equals 3, way down. So this is a position function. It's modeling how high an object is after t seconds of being dropped off a 225-foot building. What I care about, the reason I care about this, what we do with this is we want to find, for example, how fast the object is falling, how fast the object is accelerating. So we talk about something called average velocity. Versus instantaneous velocity. You guys know what velocity is or how to calculate it? Velocity is a distance that you go over a time that you go at, right? It's like speed, except it has a direction. Right, like miles per hour. Right, miles per hour is a speed. It's a distance over a time. How many miles you go over an hour. So average velocity is calculated by the change in position, how far you've gone, divided by the change in time. Instantaneous velocity is calculated by the derivative. It's taking this change in t and letting it go to 0. That's what a derivative is. It's slope, but you let the bottom go to 0. You let delta x go to 0. So let me give you an example with this function here. So I guess we'll call this. So for s of t equals 225 minus 16t squared, find the average velocity between t equals 0 and t equals 3.
Just plug it in.
You just plug it in. Okay, the idea is velocity is like a slope. You do change in your function over change in time. So the average velocity between 0 and 3, you'll do s of 3 minus s of 0 over 3 minus 0. It's just like a slope. Usually do final minus initial. I actually calculated the numbers here. S of 3, when you plug it in, you put 3 in here, you should get 81. S of 0 is 225 over 3. So altogether, when you divide this out, you get negative 48. And because you're doing a change in position, this is a change in distance, this is a foot measurement, this is a time measurement, this is telling you that on average your object is falling 48 feet per second. It's negative because you're going down. Compare and contrast. So let's do the same thing, but instead of doing average velocity, instead of finding
Instantly.
a change over a change, let me take the delta t go to 0 and do instant velocity. Find instantaneous velocity. Find an instantaneous velocity. Let's do at t equals 3. So instantaneous velocity or instantaneous rate of change is a derivative. So I'm going to have to calculate ds dt. So how do I do that?
Cancel out the constant.
Use your power rule, right? 225, if you do the derivative of this first part, you get 0. If you do the derivative of negative 16t squared, what do you get?
Negative 32t.
But I want the instantaneous velocity at t equals 3. So you plug it in. By the way, the notation for that is to put a little t equals 3 outside of a vertical bar. This is the instantaneous velocity at t equals 3. You do that by plugging in 3, you get negative 96. So why do you suppose is this bigger than this?
It's accelerated.
Vertical versus
See, this guy, the first guy, found the slope of this line here. Right, between t equals 0 and t equals 3, I found the slope of that line. But the second guy found the instantaneous rate of change, the instantaneous velocity, which is actually a tangent line. So it's like if you're driving a car. Right? If you start at 0 miles per hour and you end up at 50 miles per hour, your average is going to be in between there. Here we started out at 0 feet per second and we got to 96 feet per second, but my average is going to be somewhere in between. So instantaneous is different than average. Anyway, I'm done. Whatever. We'll review this on Monday. Okay, I'll do an example for you.